Hello, this is Dr. Armand bringing you another exciting lecture in X-ray crystallography. Today we'll be talking about the brief history leading up to the modern day X-ray crystallography. So we're going to be talking about history from the 17th century up to the beginning of the 20th century. And then the video homework that you have will cover the other 100 years from the early 20th century to the early 21st century. So sit back, relax, and enjoy the show. One second. So today we're going to talk about X-ray crystallography, a brief history. And so X-ray crystallography deals with crystal growth, X-ray diffraction, and crystal structures. These are the three main components of X-ray crystallography. So we'll be talking about crystallization techniques, the theory behind X-ray diffraction, and the theory behind crystal structure solution as well. So crystallography, if we break it down, crystalline means frozen drops, grapho means rise. So we're talking about how crystals are written. And crystals or crystallography involves solids with an orderly array. So this is the arrangement of atoms in solids. And this branch of science deals with the formation, structure, and properties of crystals. So formation means how they are crystallized, structure means how these atoms are frozen in three-dimensional space. And depending on how they're frozen, they give different properties, such as polymorphic, absolute configuration, etc. And so crystallography is a science that deals with this type of structural information. And these crystal structures are, as we'll see later, categorized into what's called different crystal lattices. So a crystal, again, it's an orderly array of atoms that has a periodic repeat unit. So the only difference between the atoms and the crystal is just translation. So you just keep on repeating the same thing over and over in 3 dimensions. And it's an ordered array. It's called a unit cell. So these unit cells get repeated in 3 dimensions. The exact same box just gets repeated over and over and over again in 3-dimensional space. And these unit cells are defined by 6 what we call lattice parameters. So these are called lattice parameters. And so the lattice parameters are the lengths A, B, and C, and the angles alpha, beta, gamma. And you can remember the angles because alpha stands for A, which means it's the angle between B and C. Beta stands for B, which is the angle between A and C. And gamma stands for C, which is the angle between A and B. And so these lattice we refer to as lattice parameters. And crystal systems are formed by restrictions in these lattice parameters. So if we restrict certain lattice conditions on the lattice parameters, we get different crystal systems. To give you an example, cubic is when A equals B equals C and alpha equals beta equals gamma equals 90. So this is some restrictions we place on the lattice parameters, which is consistent with the cubic crystal system. And we'll talk more about this later on in the course. So the first kind of observation into crystalline solids began with Johannes Kepler in the 17th century, where he was observing crystalline water, aka snowflakes, and he observed that these snowflakes had hexagonal symmetry. And snowflakes are spherical, contain spherical water molecules. And so based on his observations, he conjectured that cubic closest packing of a spherical solid should lead to the highest packing density, which means that most of the space is going to contain the spherical solid and minimize the amount of voids in the packing. And so snowflakes actually have hexagonal symmetry, meaning they have symmetry that looks similar to a hexagon, and many metallic solids have hexagonal symmetry, and usually they pack as hexagonal closed packed unit cells. So they pack in a hexagonal shape. And cubic closest packing, referred to as face-centered cubic, contains spherical atoms on the corners and on the faces of the unit cell. So here we have this cubic unit cell. We have atoms on the corners and atoms on the faces. And this maximizes the efficiency of the packing. And so when we look at it on a atomic level, you see that the atoms are best or most efficiently packed when it's in a face-centered cubic unit cell, because only 26% of the crystal volume is voids. That means the other 74% is occupied by the solid. And this is what Kepler's conjecture said: the best you can efficiently pack something is 74%. And if you click on this link later, it actually goes a little bit more in detail into Kepler conjecture. So I would strongly recommend that you watch this lecture. Now, a little bit later on, in the middle part of the 17th century, we had another, he was actually, I think he was a monk maybe, or some kind of church official. He lived in Denmark and Germany, and he's considered the father of modern geology, which is Nicholas Steno. And Nicholas Steno developed the law of constancy of interfacial angles. And this was what he came about by observing quartz crystals. And he looked at these different quartz crystals and noticed that the angle between two adjacent corresponding faces is all the same with any solid chemical or mineral species that are constant and characteristics of that species. However, he did note that the size and shape of the crystal depended on the crystallization. So again, if you have two faces of a crystal, the angle that face makes is the same for every two faces every two faces within that crystal. So for example, we have a hexagon down here. We see that these two faces, the angle is 120, and these two faces as well, the angle is 120. And so I have this little brief link on Steno's law too that you can look at to get a little bit more information on Steno. So he just explained to us, or observed, that adjacent faces have the same angle between them. Oh, actually, yeah, he later became a Catholic bishop later on. So we have Kepler, which stated that spherical molecules, the spherical solids, the best they can pack is 74% packing efficiency. And this is usually denoted by usually packed based on the cubic close structure, which is face-centered cubic. And then Nicholas Steno comes about and says adjacent faces have the same angles within the crystal. The only thing that changes is the size and shape of the crystal depending on the crystallization conditions. And then we have the father of modern crystallography, Abbe Rene Juste Howe, and he was actually a canon of Notre Dame, which was the building that burned down a few years ago. And he's actually who started this type of study called crystallography. And what led him to create this new branch of science was that he was amazed about the apparent lack of order in crystals compared to plants. So if you look at a rose, each rose is the same. You know, for particularly if you have a red rose, every red rose looks the same. Every acorn looks the same. Every leaf on a tree looks the same. So there's a lot of order in living things. However, when he looked at a stone, the stone could be the same substance, but it would give different types of structures. Some could be cubes, some could be prisms. And this happens without even changing the composition of the substance. You get different types of structures of stone. And so this structure of crystals, he determined, was regulated by some type of basic laws. And this is where crystallography became a science. And so he based crystals off of their shape of the solid. And so he looked at calcite crystals and determined that crystals can be derived from their primitive form. And he gave 6 types of primitive forms of these calcite crystals. And they're shown here: parallelepiped, octahedron, tetrahedron, etc. And that the angles within these crystals are a function of the chemical composition. So the angles between the parallelepiped sides or the octahedrons were based on the chemical composition of the crystal. He also determined the law of rational intercepts. So he said the faces of the crystal of the same substance don't just arbitrarily occupy a position, but must meet certain criteria for it to be a face, and this is expressed as rational numbers. So it just doesn't have a face just for the sheer fact of having a face. There are certain laws that it must comply to have a particular face on a crystal. And this was actually the forerunner of what we call Miller indices and Bragg lattices, which we'll talk about later. And so these were his sketches of the 6 primitive forms, which is actually the groundwork for what we later call unit cells, periodic lattice, and symmetry. This is kind of the forerunner of all of this that we'll learn throughout the course. Then comes along Louis Pasteur, who looked at how these different types of crystals could affect the plane of light. So what he looked at especially was sodium ammonium tartrate and its optical activity. And slight differences in the internal structure would manifest itself in the external structure. So when he crystallized sodium ammonium tartrate, there are 2 types of chiral isomers of sodium ammonium tartrate, the left-handed and the right-handed crystals. So we have left-handed crystals and right-handed crystals, and these have different physical shaped crystals. This is the left-handed, this is the right-handed. These are physically, they look different. They're not the same type of actual physical crystal. And so when you crystallize a solution of sodium ammonium tartrate is crystallized from a solution, you get what's called a racemic mixture, which contain both the left and the right-handed types of crystals, which developed what's called a racemic mixture, and it was optically inactive, so it wouldn't affect polarized light. But he noticed that you could actually separate physically, pick out all the right-handed crystals, pick out all the left-handed crystals, and he noticed that those individually were optically active, but together they were inactive. And this is based at the chirality of a crystal is based on the arrangement of atoms in the molecule, not the arrangement of molecules in the crystals, which is referred to as polymorphism. So different chiral substances could give different types of optical activity. So what is optical activity? You have unpolarized light, you have a polarizer, you rotate it a certain direction, and the crystal will, the substance that is optically active will disturb the polarized light or interact with the polarized light. And I have here a brief video on optical activity of sugars, which is kind of cool, so I'm going to show that for you. Let me stop the share. Resume.
There's no chemical reaction taking place here. So why is it that the liquid in this flask appears to light up when I place it in front of this filter? Well, I have a backlight, in this case an OHP, and I'm blocking all of the light that isn't passing through this filter with a piece of cardboard here. This is a polarizing filter I borrowed from the physics department. There's a second polarizing filter mounted to the front of the lens. So in theory, there shouldn't be any light coming from the OHP getting through to the back of the camera. The physics departments are probably going to have some of these filters lying around. They're used for showing things like stress patterns in plastic. You could either mount another large filter directly in front of the light source, or you could pass out smaller filters for your viewers to hold. This is a solution of sucrose. It's a chiral molecule and it's dextrorotatory, i.e. it rotates plane polarized light to the right, so it's now able to pass through the second filter. Other sugars, like glucose and fructose, are chiral too. Glucose rotates light to the right, hence also been known as dextrose. Fructose, which is sold in supermarkets as fruit sugar, rotates light strongly to the left, and is also lesser known as levulose. But have I just added a glucose solution or a fructose solution? Both look the same. However, if you turn one of the filters back and forth, you can see our solutions are rotating in opposite directions. The one on your left is fructose. Now here's a cool extension. This solution here started off exactly the same as the sucrose solution on your right. I added a few drops of lemon juice and then boiled gently for about 5 minutes. Sucrose is a disaccharide of glucose and fructose. What I've done is to begin hydrolyzing it. We now have a mixture of sucrose rotating right, glucose rotating right, and fructose which rotates strongly left. Watch as I rotate. The solution in the center now rotates somewhere between the other two. Left hydrolyzing long enough, the solution will begin to rotate left, hence being known as invert sugar syrup. Invert sugar syrup is highly prized by the food industry because compared to sucrose it's sweeter. It has a lower water activity, which means it has a longer shelf life, and also it's less prone to crystallization. The reaction in industry is actually followed by polarimetry. I've had these flasks for a few weeks, so they'll keep long enough for a whole year group to see. You can however see that the sucrose has begun to crystallize, whilst the fructose and the partially hydrolyzed sucrose have not. One of the best reasons to show this demonstration is that it draws out the point that chirality is a property of the whole molecule, not just a sum of the individual carbon atoms within it. Because glucose rotates to the right and fructose more heavily to the left, you would expect sucrose, which is made up of the two subunits, to rotate to the left. As we have seen, it does not.
So that was just a brief video showing you how different sugars give different optical activity. Now we're going to focus on radiation. So first we have to talk about Max von Laue, who is like the forerunner of diffraction of X-rays. And just to let you know, X-rays were discovered by Roentgen in 1901. He received the Nobel Prize for it. Now, Max von Laue is well known for the diffraction of X-rays by crystals. He won the Nobel Prize for this in 1914. He proposed that the X-rays were produced by the elastic scattering from electrons. So the incident electrons that are scattered, which means deflected by the original path by atoms in the specimen in electron fashion, release a characteristic X-ray with no loss of energy. However, as we'll come to see later on, the scattering from electrons is actually inelastic scattering. And there are two types of inelastic scattering. There is of X-rays. So he proposed that it was elastic scattering. So as the incident electrons that are scattered are deflected from the original path by the atoms in the specimen in elastic fashion. So there's no loss of energy in the X-rays. However, what we know is that it's inelastic scattering of electrons. And there are two types. There's continuous emission of X-rays. So as the instant electron comes in, as it gets near the nucleus, it slows down, releasing photons of X-rays. And this continuous spectrum is called Brimmer's straw Hall lung. Other type of incident electron scattering is the incident electron comes in, it hits an electron on a lower energy level, that electron is ejected, then an electron from a higher energy level, such as second energy level, cascades down to the first energy level, emitting a characteristic X-ray of a particular wavelength. Another thing that can happen is when this X-ray is emitted, it's going to hit an electron in a higher energy level, causing that electron to be emitted, called an Auger electron. So here we have X-ray tube. It produces X-rays. It strikes the crystal. And wherever it strikes the crystal, you get the pattern of diffracted X-rays on a photographic film. So how do electrons scatter? There are many different types of ways electrons can scatter, but mainly you have an incoming electron come, it hits the sample, it produces secondary electrons, which are a result of an electron passing near an atom, that it imparts some of its energy to the lower energy electrons that are in the K shell, which become ionized and leave with a small kinetic energy. There's also backscattering electrons, so they can collide with an instant electron colliding with an atom there, which is perpendicular to its path. It gets scattered backwards. There's also, we talked about Auger electrons and X-rays. There's also cathode luminescence. So the incoming electron beam causes the material to fluoresce as it returns to its ground state, producing either UV, visible, or infrared radiation. Now, what we're mainly interested in is the incoming beam hits the sample. It causes the inelastic scattering of electrons. An electron is emitted. Another electron relaxes down, causing an X-ray to be produced. And there are different types of metals you can use to produce different wavelengths of X-rays that we'll talk about later. So the way Max von Laue explained the diffraction of X-rays is that the crystal acts as a diffraction gradient because it has regular arrays in the crystal, which are planes of atoms. So a crystal, if you think about it, it has, like, if you take a stack of crackers, each cracker is its own plane. And you can imagine on that plane, it has a certain number of atoms on it. And as the X-rays hit the atoms, it diffracts. But since we're dealing with crystals, which is like a very tiny, has a very tiny, very small diffraction gradients in it, we have to use a small wavelength photon to allow it to interact with the small spacings in the crystals. And that's where X-rays come in. X-rays are small enough that they can interact with the diffraction gradient, aka those crackers that are stacked on one another. The spaces between them, they can interact with the atoms on those planes. Now, the initial idea of how this works is that the crystal absorbs the primary X-ray and then emits a characteristic diffracted X-ray. And this was first shown using copper sulfate crystals, and you can see where the diffraction spots were observed on a photographic plate. So as the X-rays carry them in, according to this first initial theory, the crystal would absorb the primary X-ray, diffract the characteristic X-ray, producing a pattern. These are what some of the first diffracted X-ray patterns look like. Very simple ones because they use what we call high symmetry inorganic compounds like copper sulfate to develop the diffraction pattern. Now, then comes along a father-son duo, William Henry Bragg, which is the father, and William Lawrence Bragg, which is the son. And they show how you can use the scattering of X-rays by crystals to investigate the structure of the crystal. And this is what they won the Nobel Prize for in 1950. And I think it was the son more than the father that actually derived the method for determining or investigating the structure of a crystal. And so William H. Bragg kind of initially thought that X-rays particles travel through the alleys in the crystals. Remember, these crystals have atomic planes or planes that contain atoms in it, and they have a certain amount of spacing within it. So just imagine you have a stack of crackers. There's some space between the crackers. And so that's where he thought the X-rays travel through the crystal. But it was his son who actually suggests that wave interference of X-rays reflected from the crystal planes generated the diffracted X-rays. And he developed what's called Bragg's law to describe this phenomenon. And Bragg's law is the foundation for modern X-ray crystallography. So you have an incident beam of X-rays which is produced by a source. And we'll talk more about how these X-rays are produced. We mentioned it somewhat when we talked about Max von Laue, but we'll talk more about it later on. It strikes the atoms in the plane, and they get reflected, and those reflected or diffracted X-rays are picked up by the detector. So let's investigate this Bragg's law a little bit more so we can understand it a little bit better. So again, Bragg's law is n lambda to the sine theta. Lambda is the wavelength of the X-rays, incident X-rays. And depending on the type of source, it can be two types. Or two common types are a copper source, where the X-rays have a wavelength 1.54 angstroms. And molybdenum source, which is another common one for small molecules. X-rays have a wavelength 0.71 angstroms. So the wavelength is pretty much set. The incident wavelength, the incident X-ray wavelength is set by the source you use to generate those X-rays. So common ones for small molecules are copper and moly source. We'll touch on those a little bit later as well. So as the incident ray comes in, it strikes the atomic planes, diffracts the X-rays, and the angle between the incident X-ray and the surface of the crystal is called theta. Now, the distance between the planes is referred to as d-spacing. So you may hear that in your reading. D-spacing is the distance between these atomic planes, or what we call the diffraction gradient. N is an order of reflection. So in crystallography, this is always set to 1, because higher order reflections are the same as first order reflections on parallel planes. So for example, the second order reflection of 100, which is a plane, 100 is a plane, the second order reflection is the same as the first order reflection of 200. And so when you have constructive interference of these X-rays, you get diffraction spots. So when these waves interfere constructively, you get a resulting diffracted X-ray, and the image or these spots show up on an X-ray detector, which in the early days was a photographic plate. Now I want to show this one last video involving Bragg's law animation so you can see how it works. Not 1992, it's 1912 actually. That's a typo. A few things here. The X-ray source is where you produce the incident X-ray beams. Again, the source for small molecules is typically either copper source, which the X-rays have a wavelength of 1.54 angstroms, or a molybdenum source, where the approximate wavelength of the incident X-rays is 0.71 angstroms. And again, the detector in the old days was a photographic plate. And then we have our crystal, which is the atomic diffraction gradient, which contains planes of atoms that diffract the X-rays. The d-spacing is the distance between the atomic planes. And by the way, the distance between the atomic planes is inversely related to the angle of the incident X-rays and the atomic plane. So they're inverse. So a high theta is a small d-spacing. A small low theta is a large d-spacing. what you're seeing here is that the X-ray source, you see that the X-rays being produced are in phase, so they constructively interfere. Then they strike the atoms in the different planes, and now you'll notice that they're out of phase. So the detector is at such an angle that the diffracted X-ray beams are out of phase, so they destructively interfere. So since the X-rays destructively interfere, the only thing you observe on the photographic film is the spot from the incident X-ray beam. So the scattered rays do not form any diffraction spots because the waves are out of phase. They destructively interfere each other, so no diffraction pattern is observed. So what you saw here is that the X-ray source, the angle at which the incident rays hit was changed so that to make sure both rays were in phase being emitted from the X-ray source. Now the detector is also moved so that the theta abides by Bragg's law with the d-spacing of the atomic plane. So again, the source and the detector were moved to make sure they abide by Bragg's law, n lambda equals 2d times theta. So now you'll notice that the waves are in phase now, so they're constructively interfering. Again, when waves are in phase, they constructively interfere. So since the second ray must travel the extra path from O to B, that's where we get the 2d sine theta from. And for crystallography, this integer multiple that's multiply of the wavelength is set to 1, because we mentioned earlier in the lecture. What you're seeing here is that when the incident rays hit the planes of atoms, when they scatter waves are in phase, we produce a diffracted image with spots of where the X-rays, incident rays, X-rays came in, where they hit atoms on the planes. You get these diffraction spots from these constructive waves that had constructive interference. They were in phase with one another. So just wanted to give you a little bit of overview of the Bragg duo, so you can see their law in action. So here I just want to show you some of the early crystal structures that were solved. You can see most of these are inorganic salts, because inorganic salts were very ordered, high symmetry solids, so the diffraction patterns were very simple. So they were very easy. Easy is a relative word to solve. Now, nowadays, for example, myself, I spend most of my time solving organic crystals of organic molecules. But back then, inorganic salts were some of the easiest material to crystallize, to get crystals big enough to get diffraction patterns for. And so that's why some of the early crystal structures were just inorganic salts. So that concludes today's lecture on just a brief introduction of the history of crystallography from about the 17th century to the early 20th century. So you can see the buildup that led to the modern crystallography that we have today. So I hope you enjoyed the lecture. If you did like the lecture or you learned something new, make sure to hit the like button. And on that note, Dr. Armand signing off. Until next time.